those points never get removed. Once they're frozen as breakpoints, they never get removed with it. So trying to come up with an easy way. Huh?
Plus, there's a continuum between 0 and
There's no continuum.
the first breakpoint, and a continuum between the last breakpoint or 1 and 1, because those portions have never been given.
They're going to be.
Well,
You tell me, give me a point epsilon here. It's either going to be one of the breakpoints or it will be removed.
well, as many steps as you go, there ought to be. But you're right.
Well,
It's called a Cantor dust, isn't it?
the Cantor set, yeah.
Cantor set.
The one, your first breakpoint is of the form 1/3 of the k. As k gets progressively larger, so that gets progressively smaller. Maybe somebody could research how to express the surviving numbers in the Cantor set as ternary decimals. It has something to do, like 0.1, you can express as like that, right?
Would be like writing
0.999 decimal.
It's equivalent.
So if you agree to express ones as this, I don't think numbers in the Cantor set can have ones in them. That it's all kinds, it's like 02, 02, 02, and just zeros and twos in the ternary expansion. But the point is, then you do that cardinality argument. You have arbitrary strings of ternary decimals, and you can show that there's uncountably many points, which means that surviving points are uncountable. But the surviving points apparently have no length, because you take away all of the length. So it's an uncountable set with it's an uncountable set with no length. So now how can we engineer a function? What if we just had f of x be 0 on the parts removed and x on the parts that stay? Then we would have this horribly discontinuous function. It would be 0, but it would be hopping around all over the place. But the set on which it did the hopping would have a measure 0, and it should be integral. It would certainly be Henstock-Kurzweil integral, right? We could figure out a mesh function that would capture all of those things, and then argue that the total contribution to the integral, as we did for the Salt-Pepper function, the total contribution is 0. And everywhere else on set of measure 1, it's 0, right? Something like that. We'll have to think about that. So, would you read a little bit about the Riemann integral for Thursday? The Riemann integral is going to go just the same way. So we'll get into more of these interesting issues here. I hope you think they're interesting. I'll research the Cantor set, and I'll write up the what was I going to write up but then you want something else. The existence of the Lebesgue, the existence of the Lebesgue number, I like that. And I'd like to prove the theorem that allows you to commute taking limits and integrating. There's one for the Cauchy limit. When is it possible, for example, to this is what you typically like to do to integration theory. If you have an integral of fn of x dx, you take the limit on the outside as n goes to infinity. You want to know when is that equal to the limit on the inside. you'd like a theorem that addresses that. That's a convergence theorem. When can you commute integration taking limits? So let's do that for Thursday. Somebody like to research this and prove that for Thursday? It's in the chapter. You know, what has to happen? Fn has to converge uniformly to F. F has to be continuous. These are continuous. They're continuous, so they're both Cauchy integrable, and you show that the integrable limits are linearly integrals. So, would somebody like to do that? Dave, don't do that. You're not even taking
Yes,
notes.
I am going to work on it.
All right. It's I think demonstrated on the board. Okay, so you present that on Thursday, and then we'll do a little bit of the Riemann stuff. And it'll be easy because, pardon?
I've already looked at that.
Oh, sure. If you want me to write this stuff up,